These diagrams are from Harvard physicist Lisa Randall's 2006 book, Warped Passages. According to Dr. Randall and her Johns Hopkins collaborator, Dr. Raman Sundram, our universe may well exist within a higher fourth dimension of space. However, unlike the flat geometry we're used to, the fourth dimension in their model would not be flat, but would most likely exhibit negative curvature. This warping of the fourth spatial dimension does help account for gravity's weakness and fits the mathematical models proposed by string theory. Note that in the diagram on the left, she indicates the fourth spatial dimension as the fifth dimension. This is simply because she's including the time dimension. On their model, all of the slices in the diagram on the right represent parallel three-branes. In other words, they represent spatially three-dimensional universes like the one we live in that are parallel to one another along this fourth spatial dimension. Randall and Sundram proposed that the gravitational force is the only one of the four fundamental forces that dramatically changes from one three-brane to the next. The other fundamental forces, since they're typically mediated by open-loop strings and confined to their respective universes, they may vary slightly in proportion to the change in gravity, but they're still stuck to the wall of each three-brane, as Dr. Gross described them. The weak brane in their theory represents the three-brane universe we live in, where gravity is weak compared to the other fundamental forces. By postulating another universe parallel to ours where gravity is much stronger, they suggest this may solve the hierarchy problem. Let's listen to Dr. Randall's comments on this theory.
But for me, I have to say the most compelling reason to think about extra dimensions is that they actually seem like they can explain phenomena, observable phenomena in our world, in ways that we just don't have unless there are extra dimensions of space. Well, one that I focus on is this question of the weakness of gravity. Gravity probably doesn't seem all that weak to you, but we have the entire Earth acting on us. If you had, for example, a magnet, it can pick up a paperclip. That's to say, electromagnetism is so strong that a tiny magnet can compete with the entire Earth, and the fact that you can jump up and down or whatever means that gravity actually isn't all that strong. And
so how would that affect the existence of other dimensions?
Well, it turns out that this is a very difficult problem to understand unless there are extra dimensions. People have been working on this quite seriously for about 30 years, since the standard model of particle physics was finished. That's the theory that describes the known forces in matter. And this question of the weakness of gravity has been a real bugbear for that theory, how to explain that. Now, if there's an extra dimension, just in sort of a picture, what you can imagine is that gravity is strong elsewhere in the extra dimension, and we're kind of seeing just the tail bit of gravity. Where we are, it's weak, although it is quite strong in this other location in the extra dimension. And we actually, my collaborator Raman Sundram and I actually found a theory where that actually naturally happens, that gravity is weak here, but really strong elsewhere.
In her book, Dr. Randall suggests several methods of reducing higher dimensions to lower dimensions to aid in our understanding. These include slicing, projection, holography, and sometimes just ignoring a dimension. We've been ignoring the dimension of time through most of this video series thus far, and now we're going to ignore one of the basic three spatial dimensions as well. This is how we can imagine our vast three-dimensional universe as a three-brane. We're basically just flattening it into a thin two-dimensional membrane when we ignore one of its basic dimensions. But then by calling it a three-brane, we're reminding ourselves that even though it looks flat, it still represents our entire three-dimensional universe. Lest you question the validity of this method, on page 30 of Warped Passages, Dr. Randall says, "This practice is not scientific fraud, but a way of disregarding the clutter of superfluous information." And she's right about that. And while the picture includes a boundary, since we're discussing the entire universe, that boundary would be at the Hubble length or further from the center of the disk. Scientists don't know whether the universe actually has an edge or boundary, but the answer to that question doesn't really affect our understanding. In this slide, I'm expanding on the diagrams in Dr. Randall's book. Again, we're ignoring one spatial dimension along with the time dimension. Since the fourth spatial dimension on Randall and Sundram's model has negative curvature, it's represented in the shape of a trumpet. Isn't that just like God? He always did like trumpets. Randall and Sundram's weak brain and gravity brain fit this model nicely as they consider the existence of a gravity brain that has a stronger force of gravity than we experience here. On their model, more than one three brain can exist along this fourth spatial dimension, separated by what Dr. Randall calls, on page 397 of her book, a modest distance of only 10 Planck lengths. This is an incredibly small distance. Here is where the term parallel universe can be used fairly accurately. The weak brain and the gravity brain are parallel to one another. But we dare not refer to parallel dimensions. Remember, dimensions are always perpendicular at right angles to one another. Most of us have had to measure something in millimeters and know how small that distance is. 10 Planck lengths is equal to 1 times 10 to the negative 34 millimeters. However, this is measured along a fourth spatial dimension, so other three brains are not something we can easily discover. Yet they're certainly plausible and discussed among theoretical physicists. Many physicists have suggested that we live in one universe with an infinite multiverse of parallel universes. This sort of thinking gave rise to popular old TV shows like Sliders, where each episode saw our heroes sliding from one universe to another, encountering vast differences on each version of Earth. And even though the concept of an actual infinite is something that can't exist in reality, this sort of thinking still captures the minds of many. But remember that what differs in this model along the fourth dimension is gravity. If gravity becomes too great on any given three brain, the stars, planets, and galaxies would be drawn toward one another so rapidly that the three brain would implode. Conversely, if gravity were too weak within a given three brain, its components would retreat from one another so rapidly that the three brain would explode. So the number of parallel universes that can exist is limited by the curvature of the fourth spatial dimension, and of course by God's creative genius. Note that the space between the brains is called the bulk. This bulk is a very important part of God's design, as we will see in future videos. Let's return to Randall and Sundram's model, which includes a fourth spatial dimension. Their model does explain the weakness of gravity in our universe by postulating a gravity brain universe with stronger gravity than we feel here. It succeeds in that way. And yet in our universe, as Isaiah tells us, even youths shall faint and be weary, and young men shall fall exhausted. The effects of gravity in our world are felt by those in the best physical condition. In our universe, most of us who have managed to live our number of years have also noticed that gravity has a cumulative negative effect on our bodies. As I've gotten older, the bicep muscle on my arm that I once bragged about as a teen doesn't defy gravity as it once did. And if I strike the same pose when I get even older, like many of us, I'll probably begin to notice more skin hanging down from my arm than I ever saw pushed up by my youthful bulging muscle. As we age, the movement of vertebrae in our spine wear away the discs that separate those bones, leading to arthritis and pain. Even my hair has moved from the top of my head down to my chin as I've aged. Okay, all right. I can't really blame that one on gravity. So this model does help to explain the weakness of gravity here when compared with the other fundamental forces. But even so, gravity still has a great effect on each one of us. What you may have figured out by now is that the existence of a gravity brain doesn't preclude the possibility of one or more universes with even weaker gravity than we experience. Can you imagine living on a three-brain Earth, where gravity is perfectly balanced to keep your feet on the ground while avoiding the negative side effects that cause your body to deteriorate? That's just what God promises us. But they who wait for the Lord shall renew their strength. They shall mount up with wings like eagles. They shall run and not be weary. They shall walk and not faint. But let's consider the other option. Can you imagine living on the gravity brain, where gravity is even stronger than it is here? Biblically, such a place exists, and Jesus talked about it even more than he talked about heaven. But he did so to warn us that it's not a place that God desires anyone to inhabit, even though many will choose to go there. Most Christian teachers describe heaven as a place that exists far beyond the farthest reaches of the known universe. They also describe hell as a place deep within the bowels of the earth. But what we've learned here from the physics of string theory is that another possibility likely exists that explains their location even more clearly than we've yet been able to understand. Let's look at another bit of evidence that it confirms a fourth spatial dimension. According to NASA, dark matter makes up about 27% of the matter in the universe, while dark energy accounts for 68%, leaving only 5% for visible matter as we know it. Sometimes the terms being used can be confusing. Remember Einstein's most famous equation, E equals mc squared? In that equation, E stands for energy, m stands for mass, and c is the speed of light. Mass is sometimes called matter, and the terms are often used interchangeably, but technically, matter is an umbrella term that includes both mass and energy. They're essentially the same thing, only differing according to their speeds of vibration. So you will also hear statements like, dark matter makes up about 85% of the total matter in the universe, which is what you'll read on the U.S. Department of Energy's website. They're just combining the 27% dark matter in the form of mass and the 68% dark energy figure. This actually comes to 95%, but I suspect they take 10% off the top since they're just estimates. What matters most about dark matter, though, is that we know of its existence only through the gravitational effects it exerts on our known universe, such as gravitational lensing. This is very important since we know that gravitons are one of the few subatomic particles that can pass through the bulk between parallel three branes. Scientists are busily trying to account for dark matter by postulating hypothetical particles within our three dimensions of space. Yet the presence of one or more nearby galaxies in a direction we don't see, along a fourth spatial dimension, could account for these gravitational effects nicely. Dark matter takes its name from the fact that it neither emits nor reflects photons. Therefore, it doesn't appear visually to any forms of detection. Dark matter is only, literally, detected via gravity. What is especially interesting is that we detect what are called dark matter halos with galaxies, including our own Milky Way. The diagram on the left shows a galaxy at the center that is surrounded by a dark matter halo. But it isn't really just surrounding the galaxy, rather it's superimposed upon the galaxy. Where there is more actual matter in our universe, there's also more dark matter found. The photo on the right has been artistically altered to remove the galaxy and to show only the dark matter halo by displaying it as a blue fog. But remember, it doesn't really emit blue light any more than it does any other color of the visual spectrum. The presence of parallel galaxies, however, each of them drawing gravitons through the bulk, can help explain why our universe continues to expand. In fact, the fact is that the expansion of our universe is actually accelerating, rather than our universe slowly collapsing back in on itself. In this diagram, I represent our universe as a three-brane and show the direction of travel of gravitons toward the same galaxy through the bulk along the fourth dimensional axis. The video you've just seen, along with the preceding video, explain a very foundational part of God's grand design. Feel free to watch them more than once if need be.